Hey there, and welcome to This Explainer. I am absolutely thrilled to have you here today. So, we're going to unpack one of the most fascinating and honestly fundamental concepts in O-level chemistry. We're exploring the incredible world of acids. And whether you realize it or not, acids are literally surrounding us every single day. They're in the food we eat, the cleaning products under our sinks, and even inside our own bodies. Today, we're going to break down the science behind them, taking a journey right from your kitchen counter straight into the laboratory. Okay, here is a quick look at our roadmap for today. We'll start with acids in everyday life, move into defining exactly what they are and their properties, then tackle the pH scale, look at 3 key acid reactions, and wrap it all up with lab safety and a quick summary. All right, let's jump right into section 1, acids in everyday life. Before we start throwing chemical equations at the wall, let's anchor this in something totally familiar. Think about this for a second. Why does a lemon taste so sharply sour? Or why does sweat taste salty? Well, that distinct puckering sourness in a lemon, that's actually your taste buds detecting a very specific chemical property. It's basically your body's built-in alarm system identifying an acid. Let's look at some super common examples. When you marinate meat with lemon juice, the citric acid in the lemon is actually actively breaking down proteins and fibers to tenderize the food. Pretty cool, right? Then we've got ethanoic acid, which is the exact chemical giving vinegar its famous zing. You've also got ascorbic acid, which you probably just call vitamin C, and even a slightly acidic compound called lactic acid hiding out in your milk. Like I said, acids are absolutely everywhere. Moving right along to section 2, defining acids and their properties. So now that we've seen the macro world of acids in our everyday lives, what actually makes an acid, an acid down at the chemical level? The crucial thing to remember is that an acid is defined as a substance that produces hydrogen ions, we write that as H+, when it's dissolved in an aqueous solution. Now, aqueous is just a fancy way of saying dissolved in water. So, when an acid molecule hits water, it dissociates or breaks apart, releasing these powerful hydrogen ions. And honestly, these H+ ions are the absolute stars of the show. They dictate basically everything about how the acid behaves. And this brings us to a really major concept, the difference between strong and weak acids. When we talk about strength, we're talking about how much of that ionization actually happens. Strong acids, think hydrochloric, sulfuric, or nitric acid, they completely ionize in water. Literally, every single molecule breaks apart to release hydrogen ions. On the flip side, weak acids, like the ethanoic acid in your vinegar or the citric acid in your fruit, they only partially ionize. Only a tiny fraction of their molecules actually release those H+ ions into the mix. Aside from churning out hydrogen ions, acids share a really specific set of core properties. Like we mentioned, they taste sour. In the lab, if you take blue litmus paper and dip it into an acid, it'll instantly turn red. Plus, because dissolving an acid in water creates all those mobile ions floating around, acidic aqueous solutions actually conduct electricity. And lastly, they have 3 very specific reactions with metals, bases, and carbonates, which we're going to look at in just a minute. Okay, let's head into section 3, understanding the pH scale. So we know acids produce hydrogen ions, but how on earth do we measure their strength? Enter the pH scale. This scale typically runs from 0 to 14. And the golden rule? Every single acidic solution has a pH strictly less than 7. No exceptions. To put that into perspective, imagine a timeline of acidity. You start with highly concentrated, incredibly strong acids down at 0, stuff like the battery acid in your car. Then, as you move up the scale to around 3, you hit weaker acids like vinegar or orange juice. Finally, as the acidity drops off entirely, you arrive at exactly pH 7. That's perfectly neutral, like pure drinking water. Basically, the lower the number, the higher the concentration of those H+ ions. Now, what's really cool is how we can actually see this invisible scale using a mixture of dyes called universal indicator. When you drop this into a solution, it changes color based on the exact pH. It flashes a deep, bright red for strong acids around 1 to 3, mellows out to a yellow-orange for weaker ones from 3 to 6, and settles on green for neutral 7. It's just a beautiful, instant visual read of what's happening chemically. All right, let's get our hands dirty in section 4, 3 key acid reactions. So what goes down when these aggressive hydrogen ions meet other chemicals? There are 3 main reactions you absolutely need to know. Acid plus metal gives you a salt and hydrogen gas. Acid plus a base gives you a salt and water. And an acid plus a carbonate, that gives you a salt, water, and carbon dioxide gas. By the way, in chemistry, a salt is just the compound left over when the acid's hydrogen gets replaced. Let's break these down one by one. First up, if you drop a reactive metal, like a piece of solid magnesium, into dilute hydrochloric acid, you get instant action. You'll see vigorous bubbling. We call that effervescence. The magnesium basically kicks out the hydrogen, forming an aqueous salt called magnesium chloride and releasing hydrogen gas straight into the air. But listen, as a chemist, you never just assume a gas is hydrogen, right? You have to prove it. So we do the classic pop test. We collect those gas bubbles in a test tube, then carefully bring a lighted splint near the mouth of it. If it's hydrogen, it ignites with a super satisfying, loud pop sound. It's definitely a lab favorite. Next is reaction 2, which is neutralization. This is what happens when an acid meets a base, like a metal oxide. Imagine solid magnesium oxide reacting with aqueous sulfuric acid. The hydrogen ions from the acid and the oxide from the base magically rearrange themselves to form completely neutral, totally harmless water, leaving behind a salt, in this case, magnesium sulfate. And finally, our third reaction. Acids reacting with carbonates to produce a salt, water, and carbon dioxide gas. So solid calcium carbonate plus hydrochloric acid gives us aqueous calcium chloride, water, and CO2. Why does this matter? Well, this exact reaction is why acids like lemon juice or vinegar are absolute lifesavers for cleaning crusty, hard water stains, which are actually made of calcium carbonate, right off your bathroom sink. We are at the final stretch, Section 5, Lab Safety and Summary. Before we wrap, we have to talk safety, because chemistry is powerful. Goggles and gloves are non-negotiable to protect against chemical burns. And as our source material strictly warns, it would be way too dangerous to taste a liquid to figure out if it's acidic. I know we talked about lemons being sour earlier, but you should absolutely never, under any circumstances, rely on a taste test to identify unknown chemicals in the lab. Just don't do it. Also, remember how we said acids react with metals to make hydrogen gas? Well, we have to be incredibly picky about which metals we use. Dropping highly reactive metals like sodium or potassium into acid is a recipe for disaster. They react explosively, which is why those specific reactions are totally banned in standard school labs. So if we can't taste them, how do we safely figure out what we're working with? We use chemical indicators. Alongside the universal indicator we saw earlier, chemists use specific dyes like methyl orange, which flips from yellow to pink in an acid, or good old blue litmus paper. These visual cues safely and instantly tell us what we need to know without putting anyone at risk. Okay, let's do a super quick recap of everything we've mastered today. Acids, they're all about producing those crucial H+ ions in water. Their strength depends completely on whether they ionize completely or just partially. They will always measure below 7 on the pH scale. And they undergo 3 predictable reactions to form salts when they're mixed with metals, bases, or carbonates. I'm going to leave you with a thought to chew on. Now that you understand the fundamental chemistry of acids, take a look around your own house later today. What everyday substances might be hiding powerful hydrogen ions? What invisible acidic chemical reactions are happening right now in your kitchen? Thank you so much for joining me for this explainer, and keep exploring the amazing chemistry all around you.